Our first use of determinants will be used in defining the inverse of a matrix. But before knowing how to find the inverse of a matrix, let's first discuss your singular and non-singular matrices. A singular matrix is a square matrix whose determinant is zero. Otherwise, it is non-singular. If say for example that your matrix A is non-singular, that is again, the determinant is not equal to zero, then we can define a matrix denoted by your A negative 1 and is called the inverse of A, which has the property that if A times B is equal to P, then B is equal to the inverse of A times P. Analogously, if B is non-singular, then A is equal to P times the inverse of B. Take note here that only matrices which are non-singular has an inverse. That is, you need to find first the determinant of your matrix in order to know that, or in order to say that you can define an inverse of that matrix. It is also clear from the previous discussion that if A times the unit matrix I is equal to A, then I is equal to the inverse of A times A. If the inverse of A times A is equal to the unit matrix I, then it is also true that A times the inverse of negative A is equal to I. It is also clear here that inverse is only defined for square matrices. Finding the inverse of a matrix A may be carried out in a number of ways. That also includes using your computers to directly solve for the inverse of a matrix. However, it is important for you to know how to solve the inverse of a matrix theoretically. The first step is to construct the matrix C containing the cofactors of the elements of A. So in this step, you're going to find the cofactors of all the elements in your matrix A. Then, the required inverse, A, can be found by forming the transpose of C and dividing by the determinant of A. So you're going to do two things here. You're going to get the transpose of C, you're going to get also the determinant of A, and the transpose of C will be divided by the determinant of A. After, the elements of the inverse of A are then given by the following. So you have your cofactor, the transpose of your cofactor, divided by the matrix or the determinant of A. So this is how you're going to find inverse of a matrix A. So let's review the steps. First, you're going to construct the matrix C containing the cofactors of all the elements of A. That is, you're going to find all the cofactors of all the elements in your matrix A. Then, you're going to get the transpose of C, and the transpose of C will be divided by the determinant of your matrix A. Then, the elements of your inverse A is given by the following. You have your inverse A matrix is equal to the transpose of the cofactor divided by the determinant of your matrix A. Let us have an example. Here is a matrix A, a square matrix A, which is a 3 by 3 matrix with the following elements. You have your matrix A of elements 2, 4, 3, 1, negative 2, negative 2, negative 3, 3, and 2. For this matrix, we are asked to find for the inverse of A. So you can find first, for example, the determinant of A. The determinant of A using your first row and finding the cofactors is equal to this one. So A, that's equal to this values here. And simplifying, you get a determinant of value that's equal to 11. Again, you can use any of the rows or column of your matrix A to find for the determinant of A. And you already thought of this one. For this example, the determinant of A is equal to 11. As you can see, this is non-zero, and so an inverse matrix can be constructed. If, for example, you found that the determinant of A is equal to 0, then no inverse can be constructed. Because as you can see, the transpose of the cofactor divided by 0 is undefined. Now, since this is non-zero, we can define an inverse of this matrix. To do this, we need the matrix of the cofactor C, and then we get the transpose of your matrix of your cofactors. Now let us find the cofactors of all the elements of A. In the first row, first column, we have your A11, which is equal to 2. Finding the cofactor, we have negative 1 raised to 1 plus 1 times this determinant of this 2 by 2 matrix here. So you have negative 1 raised to 2, that's positive 1, times the determinant of this 2 by 2 matrix. This is equal to 2. For your A12, still on your first row, you have negative 1 raised to 1 plus 2 times the determinant of this matrix here, composed of your 1, negative 3 and negative 2, 2. Negative 1 raised to 3 is equal to negative 1. So you have negative 1 times the determinant of the square matrix, which is equal to 4. For your A13, we have negative 1 raised to 1 plus 3 times the determinant of the square matrix composed of your 1, negative 3, negative 2, and 3. Negative 1 raised to 1 plus 3 is equal to 1 times the determinant of the square matrix. We get a value that's equal to 3. Now let's go to your second row. Let's look at first the cofactors of your element A21. For A21, you have negative 1 raised to 2 plus 1 times the determinant composed of your 4, 3, 3, and 2. Negative 1 raised to 3 is equal to negative 1 times the determinant of this matrix here. You get a cofactor that's equal to 1. For your A22, we have negative 1 raised to 2 plus 2 times the determinant of this 2 by 2 matrix composed of 2, negative 3, 3, negative 2. Negative 1 raised to 4 is equal to 1 times the determinant of this matrix. The cofactor is equal to 13. For your A23, we have negative 1 raised to 2 plus 3 times the determinant of the matrix composed by your 2, negative 3, 4, and 3. Negative 1 raised to 5 is equal to negative 1. Negative 1 times the determinant of the square matrix here is equal to negative 18. For your A31, we have negative 1 raised to 3 plus 1 times the determinant of the square matrix composed of 4, negative 2, 3, and negative 2. Negative 1 raised to 4 is equal to 1 times the determinant of the square matrix. Your cofactor is equal to negative 2. For your A32, we have negative 1 raised to 3 plus 2 times the determinant of the square matrix composed of your 2, 1, 3, and negative 2. You have negative 1 raised to 5 is equal to negative 1 times the determinant of the square matrix. Your cofactor is equal to 7. For your A33, which is our last element, we have negative 1 raised to 3 plus 3 times the determinant of the square matrix composed of your 2, 1, 4, and negative 2. Negative 1 raised to 6 is equal to 1 times the determinant of the square matrix. We get a cofactor that's equal to negative 8. So these are the cofactors of our elements of matrix A. On the first row, we have 2, 4, and 3. On the second row, we have 1, 13, and negative 18. On your third row, we have negative 2, 7, and negative 8. We're going to write these elements in a matrix, which we will define as your matrix C. The matrix of your cofactor C is the following. You have your C that's equal to 2, 4, negative 3, 1, 13, negative 18, negative 2, 7, and negative 8. On our next step, we're going to find the transpose of this matrix C. The transpose is just interchanging the rows into columns and the columns into rows. Your C transpose is equal to 2, 1, negative 2, 4, 13, 7, negative 3, negative 18, and negative 8. This is now your transpose of C. For our last step, we are going to divide the transpose of C with the determinant of A. The inverse of your matrix A, which is equal to the transpose of C divided by the determinant of A, is equal to the transpose divided by your determinant, or just your transpose of matrix C times 1 over 11. This is now the inverse of your square matrix. Of course, you can simplify this one by dividing all the elements with 11, or you can just have this one as is. That is how you are going to find the inverse of matrix. Now let's review the steps of finding the inverse of matrix. First is to find the matrix of the cofactor C. That is, we need to find all the cofactors of all the elements of A, and we write it in a matrix which we will label as C. Then we will find the transpose of your matrix C. After that one, we are going to divide the transpose of your matrix C by the determinant of your matrix A. And you get your A inverse, the inverse of your matrix A. For a 2 by 2 matrix, the inverse has a particularly simple form. If the matrix A is equal to this matrix here, which has the elements A11, A12, A21, and A22, then its determinant is given by your A11 times A22 minus A12 times A21. And the matrix of the cofactors is equal to C, that's equal to A22, negative A21, negative A12, and negative A11. Thus, the inverse of A is given by your cofactor, the transpose of your cofactor, divided by the determinant of A, which is equal to 1 over A11, A22 minus A12, A21, times the inverse of your cofactor, that is your A22, negative A12, negative A21, and A11. The following are some further useful properties related to the inverse matrix. First, we have the inverse of A is equal to A. The inverse of the transpose of A is equal to the transpose of the inverse of A. The inverse of the Hermitian conjugate of A is equal to the Hermitian conjugate of the transpose of the inverse of A. The inverse of A times B is equal to B inverse times A inverse, which you can further extend to the inverse of A times B up to G. That's equal to G inverse times dot 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 times B inverse times A inverse. Now let us discuss some special types of square matrix. Matrices that are square, that is an n by n matrix, are very common in physical applications. We now consider some special forms of square matrix that are of particular importance. The first special type of a square matrix is called your diagonal matrices. Such matrices are characterized by having n non-zero elements only in the leading diagonal. That is, on this diagonal here. Only elements of your Aij, where I is equal to j, may be non-zero. That is your A11, your A22, and A33 for this example. The unit matrix, which we have already encountered, is an example of a diagonal matrix. Another example of a diagonal matrix is this one here. You have your 1, 0, 0, your 0 to 0, and then your 0, 0, negative 3 elements. Here you see that only the diagonals are non-zero, the rest are 0. Your A11 has an element of 1, your A22 has an element of 2 and your A33 has an element of -3. Such a matrix is often denoted by your A is equal to the diagonal of 1 to -3. So instead of writing this one as a whole, we can also write this matrix in just this way. Again, you have your A is equal to the diagonal 1, 2, and -3. This is just equivalent to saying that you have this matrix here. By performing our Laplace expansion, it is easily known that the determinant of an n by n diagonal matrix is equal to the product of the diagonal elements. Again, it is easy for diagonal matrices to find the determinant. It is just equal to the product of the diagonal elements. If, for example, the matrix is the form A that's equal to the diagonal of A11, A22 up to ANN, then the determinant is just equal to the product of the diagonals, which is equal to A11 times A22 up to ANN. It is straightforward to show that the inverse of A is also a diagonal matrix given by this one. The inverse of A is just equal to the diagonal, diagonal of A over A11 or 1 over A11. Then you have your 1 over A22 up to 1 over ANN. So in here, to find for the diagonal or the inverse of a diagonal matrix, you just need to get the reciprocal or the inverse of each element of the diagonal. If two matrices A and B are both diagonal, then they have the useful property that their product is commutative. That is, your A times B is just equal to B times A. This is only true, however, for diagonal matrices. Remember, again, that this relationship is only true for diagonal matrices. Now let's talk about the lower and upper triangular matrices. A square matrix A is called lower triangular if all the elements above the principal diagonal are 0. Here, our principal diagonal is again composed of your A11, A22, and A33. And a square matrix is called triangular if all the elements above this principal diagonal are 0. For this case here, your A12, A13, and A23 are 0. Then this is called a lower triangular matrix. For example, the general form for a 3 by 3 lower triangular matrix is of this form here. Similarly, an upper triangular square matrix is one for which all the elements below the principal diagonal are 0. That is, your A21, your A31, and your A32 are all 0, except for all the other elements above your principal diagonal. So this one is called an upper triangular square matrix. By performing a Laplace expansion, it is straightforward to show that in a general n by n case, the determinant of an upper or lower triangular matrix is equal to the product of its diagonal elements. That is, for any upper or lower triangular matrix, the determinant is just equal to the product of the elements of the principal diagonal elements. That is, if you have an upper or triangular matrix, the determinant of A is equal to A11 times A22 up to ANN. So it's easy. If you just have an upper or lower triangular matrix, to find for its determinant, you just need to multiply all the elements of the principal diagonal. The inverse of a non-singular lower triangular matrix is also a lower triangular matrix. Also, the inverse of an upper triangular matrix is also an upper triangular matrix. That is, for a lower triangular matrix, the inverse should also be a lower triangular matrix. For an upper triangular matrix, the inverse is also an upper triangular matrix. Lastly, a square matrix A of order n with a property of A that's equal to A transpose is said to be symmetric. So if you have this property here for your matrix, then you can say that your matrix is a symmetric matrix.